All right, this video is a continuation on introduction to acid and bases. In this video, we'll focus mainly on Bronsted Lowry acids and bases. So, with this said, that we have three concepts of acids and bases. The first one is Arrhenius concept. The second one is the Bronsted Lowry, and the last one is Lewis Lewis concept. In this video, we're going to focus on Bronsted Lowry acids and bases. Okay, now this Bronsted Lowry concept of acid and bases, like we said, was proposed in the 1920s, so 1923. It was proposed in 1923, and it gave a very simple definition for acids and bases. Now, they said an acid, according to Bronsted and Lowry, an acid, so let's put that here. An acid is a proton donor, and a base is a proton acceptor. Good. All right, so that is a Bronsted and Lowry definition for an acid and a base. Very simple. Proton donor for an acid and a proton acceptor for a base. Okay, now let's look at an example. Let's take hydrochloric acid in water. So this is HCl, hydrochloric acid, plus water, H2O. Now, what is going to happen? We'll have H3O plus and then Cl minus. So what's happening here? You realize that the chlorine here has a hydrogen attached to it, but at the other side of the equation, there is no hydrogen there, so it carries a negative charge. Okay, so what is happening here is that we have HCl in water, this HCl, hydrogen bonded to chlorine, and you know that chlorine is more electronegative than hydrogen. And so hydrogen is going to have a partial positive charge, and the chlorine will have a partial negative charge. Now, water is also polar. What it means is that it also have a partial positive charge on the hydrogens and a partial negative charge on the oxygens. So what is going to happen is that the oxygen here has two lone pairs of electron, which it is going to donate into the empty orbital of the hydrogen after the hydrogen gave its electrons to the chlorine. So when hydrogen loses its electron, it's called a proton. It's called a proton. So this is the proton in this case. This is a proton in this case. So what happened here is at the other side of the equation, we have oxygen now bonded to three hydrogen atoms with just one low pair, and this time it has a positive charge on it. So this is H3O plus. So what actually happened is that the hydrogen here loses its electron to chlorine. So we'll have chlorine with surrounded by electrons and now carrying a negative charge. Now remember we said when a hydrogen loses electron, it becomes a proton. Now that proton is now connected to oxygen. So in this case, we'll say that HCl is donating the proton to water molecule. So HCl being the one donating the proton becomes the acid. And the water molecule accepting the proton becomes the base. So that is the Bronsted Lowry concept of acid and base. Now let's take another example. Let's take let's take ethanoic acid CH3COOH in water, and this is going to give us CH3COO minus ethanoate, and then the hydronium H3O plus. So what is happening here? The ethanoic acid has a proton on it. Let me pick a white color here. So this is the hydrogen, which is going to be the proton. So a hydrogen that could easily be loose in a molecule is what we call the acidic hydrogen. So the ethanoic acid has this hydrogen as the acidic hydrogen. Now what is happening is that it is donating this hydrogen, which will become a proton, to water molecule. So over here, we now have ethanoate. So there is no hydrogen here. However, the water molecule now gains that particular proton and becomes H3O plus. So this guy is our donor, and this is the acceptor. So if that is the case, the donor becomes the acid and acceptor is a base. So that's another example or illustration of Bronsted and Lowry acid and base. Okay. Now let's take another example, then we'll go on. Let's take ammonia and water. So this is ammonia, NH3, and water H2O. Now what is going to happen? We are going to have NH4 plus, and then we'll have OH minus. Okay. Now what is happening here is so this is ammonia NH3. Now you realize that over here the water is donating the proton, so this becomes our donor, and this is the acceptor. So we form NH4 plus. That means the ammonia has taken an extra proton and it's going to give us a dative covalent bond. So this one has taken the proton and becomes NH4 plus. Now, water molecule has two hydrogens. When it loses one, it's left with one. So that's what we are seeing here. It is OH minus. So we can see that the base is the ammonia, and in this case, the acid is the water. The acid is the water. So that is Bronsted Lowry concept of acid and base. Now, you also notice that only one reaction is used to illustrate the Bronsted and Lowry concept of acid and base, unlike we have in the Arrhenius definition. Okay, so that's one thing to take note of. Now, what is conjugate acid and base pair? Conjugate acid and base pair. So let me write that here. Conjugate acid base pair. Now let's say our Bronsted Lowry acid is HA, and the base is B minus. Now what is happening here is that the acid is going to donate a proton to the base. So we'll end up having HB, and then we'll now have A minus. Good. So this is just an illustration of a base. So A could be any compound that is having an acidic proton or acidic hydrogen. Okay. So what is happening is that This one and this one, sorry, this one and this one constitute what is known as conjugate pair. Conjugate pair. Then this one, B minus and HB, also constitute another conjugate pair. Another conjugate pair. So this is another conjugate pair. All right. Now let's take a look at HCl and ammonia. So this is HCl, which is an acid, and then we have ammonia, which is a base, NH3. What do you think the product would be? Now your guess is as good as mine. So this is going to be NH4 plus Cl minus. Okay. Now when we are considering the pair, we call this the acid because it's the one donating the proton. So this is the acid, and this one becomes the base because it's accepting the proton. Now on the right side of the equation, this one is what we call the conjugate acid. So conjugate acid, and the Cl minus is what we call conjugate base. Okay, so what you observe is that you realize that ammonia over here was the base, and then it takes a proton from HCl and becomes what NH4 plus. So when we take the pair, the HCl, HCl, and a Cl minus, so HCl slash Cl minus. This one constitutes a conjugate pair. So this is our acid, this is our acid, and this is a conjugate base. So you realize that the difference between HCl and Cl minus is just a proton. So one way we can describe conjugate pairs or acid-base conjugate pair is that they are species that differs by just one proton. So when you take HCl, it is an acid, it loses a proton, it becomes Cl minus. So the Cl minus is as a result of ACl losing a proton, so we call it its conjugate base. Okay. Now, when we take the other pair, we have NH3 and NH4 plus. So this is NH3, and we have NH4 plus. So what is the difference here? The only difference here is a proton. Now, the NH3 over here and the reactant sites lacks one proton, while NH4 has the proton. So the difference here again is the proton. So this is our base, and this is the conjugate acid. Why is it an acid? Because it has the capability of donating a proton back to HCl and to form these backs. That's why we use reversible arrows in these equations. Okay, so why don't you try this? Let's say CH3, acetic acid, and water, H2O. This is going to give us CH3, COO minus plus H3O plus. Okay. Now this let's say this is liquid aqueous, Aqueous means it is dissolved in water. All right, so what is happening here? You can see that we have ethanoic acid and water, and they are given as a product. So, what do you think is the acid and what is its conjugate base? The acid is this acetic acid, and then the conjugate base is going to be this. So, these are conjugate base. Now, over here, water is a base, and the conjugate acid of water or the base is H3O plus. So, these are conjugate acid. Good. All right. Now there are some few things that we can observe from this reaction. Now acetic acid is less than 1% ionized in water. That means it's a very weak acid. So we see that since the equilibrium is displaced mostly towards the left, so that's why you see that the arrow here is shorter than this one. That means we'll have more of these in the solution than the ethanoate and the H3O plus. So what can we say? We'll say that the ethanoate is a stronger base compared to water. So you observe that equilibrium lies to the far left compared to what we have at the product side on the right. So we'll say that C, the ethanoate. So let's write that down. CH3COO minus is a stronger base than water. What does it mean? That means that anytime we have a free proton in the solution, this one, ethanoate, has a higher tendency of picking that proton faster than water could have picked it to form H3O plus. So CH3COO minus is a stronger base compared to water. Now another thing is that H3 H3O plus or the hydrogen ion is a stronger acid compared to the ethanoic acid. So let's put that here. H3O plus is a stronger acid than CH3COOH. All right, so this also means that H3O plus has the capability of denoting a proton faster than CH3COOH. So if that is the case, the one who gives out the proton more easily becomes a stronger acid because we know that an acid or a Bronsted Lowry acid is a proton donor. So based on this observation, what can we conclude? Now we can say that a weak acid always has a strong conjugate base. So if the acid is weak, like CH3COOH, ethanoic acid, its conjugate base is a strong base. Okay, so this is weak, this is a weak acid, and this is a stronger base. Now, we also observe that water over here is a weak base, however, it is giving rise towards a stronger conjugate acid. Okay, so these are some observations that we can make from this particular reaction. Okay, all right, so basically, this is what Bronsted and Lowry acid is about. Now, watch out for the next video and don't forget to like and subscribe. Thank you.